So today we're going to start Chapter 9, and it starts with the center of mass. The center of mass is a point at which the object's total mass is concentrated. We look at the center of mass of systems of particles. Systems of particles just means there's multiple masses, multiple separate masses, right? A particle. So the idea here is if we looked at an origin, like an XY axis, and we have one mass located here, and then we have another mass located here that is equal to the mass here, and they are separated by some distance, I think we may be able to reason out that the center of mass is located in the middle. But what happens whenever we have a mass m there and then a larger mass here? Well, the center of mass is going to shift towards the location where more mass is concentrated. All right, so that would just move towards big M. Now, we will have to be able to calculate exactly where that is. And the equation that is listed on our equation sheet, there is no equation. Oh, yeah, there is. Okay. Which is going to be RCM, which is the center of mass, the location of the center of mass, is equal to the sum of M times R over the sum of the masses. Now, I'm going to use x's, so I would write it as XCM is equal to M1 times the location of X1 plus M2 times the location of M2, oh yeah, M1, plus however many particles we have up until the nth particle. And here is going to be M1 plus M2 plus M3, or dot 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 M to the nth. All right. Now, when we get out of systems of particles, we need to think about it as integration. So, just to help us out when we get there, let's just call the sum of all the masses big M, the total of all of those. So that XCM is going to equal, so if we can pull this out and just call that 1 over M times the sum of the masses times their positions from, and this is listed as I equals 1 to some letter n, or some number n. All right, and we'll see how that form starts to help us out. Now, we can have center of masses in the x direction, y direction, and the z direction. I'm sure you can figure out what that is. Okay, so I think, well, again, I'm just going to keep that for when we start doing integration. This is what's on our equation sheet. And I think this is the best way to solve them out, all right, or write it out. And again, that's for separate particles. If we have rigid bodies, where there's a constant distribution of mass, such as something like this. So if we had our x and y axes, and some oddly shaped object like that. All right, so there's an infinite number of particles in there, okay? So if we try to take one of those infinitely small sections of mass, we would call it dm. So that's the infinitely small amount of mass that is contained at any location, down to the single particle. All right, and then that is distributed over the entire surface. We'll call it the differential mass here. Now, for this, our distribution of particles, we would hope would be even. Which means throughout the object, they are approximately evenly spaced. Okay, so that would be a constant. If it's not evenly spaced, it can start to get more dense as we cover the length. All right, so that would be a varying distribution of mass. That makes it a lot more challenging, of course. So the way that we want to think about this equation, because they do not have this integration part on our equation sheet, if we go from this, I equals 1 to n of x n to n m n, okay, or I. This sum is a limited sum, so you can add an exact number of particles together. If we integrate, we have an infinite number of particles. So the sum turns into an infinite sum. And we are basically adding up all of the infinitely small pieces of masses at the location they're at. So this changes to the infinitely small mass, and this is the location of each of these little dm packets. And of course, you have the same thing for y and z. So there's no way to know the exact position of each individual particle. Something like this, what we can look at is how much mass is located at a specific, in a specific area. So what we have to do is change this around into a more useful form to talk about this area. And in order to do that, we're going to look at, so if we have, we're going to look at the density, all right? So if we have a constant distribution of mass within a certain space, it means it has a constant volume or area distribution. So for this specific shape, it's a two-dimensional plate. We're going to use different variables for the number of dimensions. So rho is mass over volume. This is three-dimensional volume. Sigma is mass over area, which is two-dimensional density. And lambda is m over a length, which is one-dimensional. Okay, so for this specific object, we're going to utilize this. So if we looked at a single area, so we're going to just look at this part of that object in this space. Okay, the total mass of this single section divided by its total area will be its density. Now, if I took a small, infinitely small little packet of mass there and divided it by the differential area, so there is a very small amount of area there. And if it's a constant density, just like, you know, talking about the different atoms, a block of gold has the same density as the individual atom of gold. So this is basically saying one single, whatever, atom molecule of whatever that object is, has the same density as the entire piece. Okay. What we're going to do is get rid of the mass. So we're going to manipulate this so that dm is equal to sigma dA. Now, what we can do is we can substitute this in for dm into this equation. Okay, so I'm going to kind of get rid of those things. So that xcm is going to be equal to 1 over the mass times the integral of x times is equal to both the differential
and the total area. So I'm going to actually now substitute this into this equation. So we have 1 over m times x, m over a, dA.
So what we end up with is these are constants. So we can pull those out of the integral. So that means this is going to cancel out. So we're left with 1 over the total area is equal to the x times the differential area. Now, this x is going to be the location of the center of the area. So you would have to figure out the half dimensions of each of them and put that with respect to the origin. So you would have to basically figure out how far over from here is it, and then how far down is it, and that's going to be the center of that single area. And again, you can do it in both directions. So we have, again, volume, area, linear densities, We're going to get used to substituting in these values into integrals. And so, and just so you know, we can utilize each of these into the same idea. Whereas if sigma is dm over dA, this is equal to dm over dl, this is equal to dm over dv. So you can do the same exact substitutions where we get, if we did three-dimensional, 1 over v integral of x dv. If we had to do a linear, 1 over L, total length of the object, integral x dl, the little segments of length. Okay, so I'm going to stop this video here, and we'll continue with this on the next video.